lectures. And so I just from the very beginning, I want to say that my educational background is condensed matter physics, not really mathematics or random access theory or something like that. And therefore, when I learned myself random access theory, I somehow learned it in such a way that I always had condensed matter pictures in mind and tried to put them in correspondence with this mathematics that random access theory offers. And in these lectures, what I will try to do, first of all, I will try to give always some connection to physics, and it is probably only 30 to 35% of the time I will be concerned with the classical random matrix theory. But as it is written here, I mean, it's not written here, it is written in the description of the course, random matrix theory and beyond. And this beyond will be, the major part of the lectures. So I think that it is really a course which doesn't have so much analogy online or in books, because usually random matrix theory means theory of ignorant and Dyson. And there is a lot of mathematics there, and quite nice, quite specific. But when we come to real world, in fact, it is very universal theory, very broad application, but still limited. Limited in the sense that it is not applicable to any situation where we expect localization effect. And Anderson localization will be, in this course of lectures, will be a very prominent guide, because I will always deviate from the classical random matrices to random matrices which are a bit less universal, but still give some important information about Anderson localization. They show this localization effect, and moreover, they is an important tool, toy method, to understand some features of many body localization. Not all features of many body localizations, but some. And this, what is more important is that random matrices are the object which allows for more analytical treatment than, for instance, indirecting systems, spin systems with disorder, and objects which usually are studied in connection with many body localization. So there will be random matrices, there will be Anderson localization, and there will be some reference to many body localization. So this is the description of the general idea of this course. And I start with very elementary things. And here you see the picture of a shallow water, in a sunny day on the beach where the water is not deep. You can see this nice picture. Then there is a completely different system, which is micro electronics, which is quantum dot, and then there is a schematic picture of nuclear physics when some fast particle collides with the nuclei, and then it is possible to study what kind of resonances appear. And so you see, this is a completely different fields of physics. This is, one can say, hydrodynamics, this is microelectronics, and this is nuclear physics, and yet random matrix theory is something that unites all these fields together. So, how does it unite? You can see different pictures. So this is the same picture of shallow water in a sunny day, and here you see some pattern, some bright pattern, and this is the mathematical object, which is the superposition of many plane waves with random coefficients and random directions. And if you compute the square modulus of this psi function, then you can map this also on a two-dimensional plot. And what you see very similar picture. You see some bright web, and then dark points, holes, and it is in apparent correspondence with one another. But then this is still this is a mathematical object. This is hydrodynamics, and then there is quantum mechanics, which is also wave dynamics. And what you can do, you can superimpose plane waves and study the amplitude of that, and not surprisingly, it gives you a very similar picture. And in order to realize it in, so to say, in the hardware, it is again this quantum dot which shows the properties similar to this superposition of random superposition of plane waves. But in order to this is quantum mechanics, but in fact the quantum dot is sort of a billiard for electrons, because there are some boundaries and electron is reflected of these boundaries, and if electron were a classical object, then we would see trajectories like this, which this is a classical picture of what is happening in the quantum dot, and that chaotic trajectory, it is because the boundary has some maybe symmetric, but not the form that allows for exact solution, and therefore this kind of billiard is chaotic billiard. And then we see, after quantization of this picture, we see things similar to what is shown here, and as I said, it is similar to what is happening in the hydrodynamics. And now, again, some reference to condensed matter theory. Random matrix actually came to attention to condensed matter physicists in in the end of 90s, in the beginning of 2000, where people produced such microstructures, such quantum dots, and study electron transport through it. So basically, here there are some boundaries, some gates produced by microengineering, and essentially this is like a billiard with boundaries, and then there is some gate voltage applied to this dot, which changes its potential, and then there are some doors where the electron can come in and can go out. And this is basically what quantum dot is. So you apply two voltages. One is so-called gate voltage that changes the potential of this dot compared to the ground. And then there is some source voltage that makes the current coming in and going out. And when people started to study such objects, they found that in fact at low temperatures, what happens is that such device is transparent, so it allows for current to go only at some specific values of this gate voltage. Otherwise, the dot is blocked, and that is known as the Coulomb blockade. So what is actually happening is the following: that in order for electrons to come more or less freely in and out, what you should have that the energy of so this dot is like a capacitor. So when electron comes in, it charges this dot, and that costs the energy. So what we know that the energy of a capacitor is proportional to the square of the charge, and so the energy written in terms of number of electrons there, it is quadratic in the number of electrons, and this dot is transparent when there is a degeneracy. So the energy of having m+1 electron here, and the energy of having n electrons inside the dot is actually compensated by the gate voltage, by the energy of electrons in the presence of such voltage, and this bias is of course linear in the voltage, and it is linear in the number of electrons. And then if the energy of capacitor and the gate voltage for m+1 electron is the same as that for n electrons, then there is a degeneracy, and electrons can come and go out freely as if Coulomb interaction is not present. So then, if you solve this equation, what you will get that your gate voltage for such a degeneracy should be some very definite values for n equal 1, for n equal 2, for n equal 3. So it is discrete. And this discreteness was observed in the experiment, and this seems to be a very trivial stuff. But in fact, when people went beyond this simple relationship and took into account that the dot is a quantum mechanical device, and it is the device of finite sizes, then there is a quantization of electrons, of electron energy, and when you take magnifying glass and look more precisely at these distances, you will find that these distances are not exactly equidistant. So then, this is the picture that explains why it is not equidistant, because there is a Pauli principle, and you fill in the dot is a quantum mechanical system with discrete spectrum, and it is filled according to Pauli principle, and if you want to, if the filling is even, and then you add one more electron, then even without any Coulomb interaction, you have to pay the energy of the distance between the levels. And therefore, in fact, the distance between these peaks in the conductance, in the transparency of the dot, it is not only like it was shown on the previous slide, it is not only 2En, the distance is 2 EC, but in fact it is 2 EC plus this delta. So if you have a very sharp peaks, so you have to be at very low temperatures where the width of the peak is exponentially small, then you can actually measure very precisely this distance between the peaks, then subtract this trivial Coulomb part, and what you will get the structure of energy levels inside. But then, as I said, this dot is not of rectangular or circular form, so it has a boundary which is complex, and the classical motion there is chaotic, and for that reason the distance between the energy levels is also random. It has some average value, but it fluctuates. And so by studying, for instance, these peaks, you can have an idea about the statistics of energy levels inside, and this is what is the subject, the important part of the subject of random matrix theory. So basically, these experiments gave a very strong push to random matrix theory, especially among condensed matter physicists and also among the experimentalists. Because I remember that before, let's say, 86, for most of you it is prehistorical time, but for me it is something that I lived with that. And before 86, in condensed matter theory, nobody almost nobody had any knowledge about random matrix theory. Because random matrix theory at that time, and even earlier, it was created in the beginning of 50s. And somehow this theory was created not because of these condensed matter experiments, but because of the experiments that I have shown here. Schematically, it is the nuclear physics. So you know that in the end of 40s, there was a great push for nuclear physics because of the Manhattan project, because of this, things like atomic bomb and then creation of new elements by bombarding atoms. So all this stuff, of course, was greatly enhanced by development of nuclear research, and then the theory which gives the most universal features of nuclear experiments was created by Wigner and Dyson, and this was the random matrix theory. But it came to, in this community of nuclear physicists, it was just the main tool. But in condensed matter, it come, some 30 years later. And then I was talking about the energy levels. So, but basically, if you consider quantum mechanics, so there is so-called quantum data. Quantum data is eigenvalues and eigenvectors. So this is about eigenvalues, how it is possible to measure it, how it is possible to make sure that this system of quantum dot is indeed well described by random matrix theory, but also there is a possibility to extract information from the same experiments about the eigenfunction, not only eigenvalues. So if you look at this picture, then there is one object, as I said, is the distance between the peaks. And the other object is the height of the peaks. And as you see, this height of the peaks is quite complex. So it is random but strongly correlated. Then people thought how it is related with eigenfunctions, and this relations is quite simple because suppose you solve the quantum mechanical problem inside the dot, and you have some amplitudes of wave function on the incoming door, and some amplitude of wave function near the outgoing door. And so you can understand that the current, the stream of electrons is proportional to the density. And the density is the amplitude of wave function. And therefore, somehow the width of the door, which allows electrons to go in and out, is proportional to the wave function when you solve the problem of the closed door. And so there is more precise formula which is in fact something like parallel connection of conductance, and so this formula tells you that the height of the peak is actually the form like this, and each one is psi squared in the point where the electron comes in and in the point where electrons go out. So basically, again, these experiments gave an access to studying the statistics of wave function, because wave functions amplitude are also random, and then it is quite interesting how, with which probability you have this or that amplitude of the wave functions, and then also correlations between them. So then it was about condensed matter experiments at low temperatures. And now there was another activity which also had random matrix theory as a mathematical tool, and this is so-called microwave billiard. So what you have some metallic plate, then the cavity, and then some antenna which inserts electromagnetic wave inside, and then you have some other probe antenna where you put the electromagnetic wave in and see how much of this wave is reflected back. So, and then it is clear that if you have some eigenstate at this energy of the microwave, then so you put the microwave with some energy, and if there is an eigenvalue of this electromagnetic problem with such an energy, then this electromagnetic mode will be excited and less electromagnetic intensity will be reflected. So each time when you hit, if you see the reflection of electromagnetic waves, then each time when you hit a discrete spectrum, then you have a drop of reflection. And then again, you have quite narrow peaks, you have random distance between them, you have random amplitudes of reflection, and you, for many reasons, you are interested in statistical properties of this amplitude of this distance. And this is again appears to be the realm of random matrix theory. Now, with such experiments, it is possible to measure the intensity at different points, and so to probe the amplitude of the wave functions. And if you have a billiard, you can do this experiment, and you see that the amplitude has some pattern which depends on the energy. So there are some places where the intensity is higher and the places where the intensity is lower, and for certain modes this picture is quite simple. It looks like regular, but for other modes, especially with high energy, you have a picture which looks pretty much chaotic. And so this was also the subject of study. In fact, such places where the intensity is enhanced is known as scars. So it is a quantum scar. So you have on the average some intensity, and then you have some scars like on the body, and this was actually some important piece of study at that time. But it is interesting that somehow the ideas which come from these quantum billiards, from these quantum scars, it went through the years and realized now as quantum scars in many body situations. So in many body situations, it is. So this is a single body. So this is one particle that is solution of the problem of one particle in such a billiard. But what people are studying now is the system of many particles which interact with themselves, and it appears that there are quite special initial configuration of these interacted particles such that the corresponding state lives long. It does not, if you create such a state, it does not dissipate. It stays for a long time. But if you take a bit different initial condition, it quickly dissipates to nothing, to some structureless state. And this is like here. So this is, if you create the state here, it will live quite long, but if you create it there, so it will be dissipated through this blue region and very quickly. And so these quantum scars are now also subject of the present investigation, and now there are experimental techniques to create such states and then to probe it after a time. So we see that these ideas which somehow created 30 years ago, they now are transformed in a much more complex situation, but also in some practical situation, because when people are talking about quantum computers, they have to know actually what happens with the state, what is the quantum dynamics of that. And it appears that this is a visualization of the ideas which are very pertinent now. Then, since I'm not a nuclear physicist, a high-energy physicist, so of course my pictures about condensed matter situations are more sort of richer. But actually, as I said initially, this random matrix theory was created in order to explain experiments of nuclear scattering. So the energetic neutron scatters of the nuclear, where there are neutrons and protons, and then like in this experiment with quantum billiard, where you have a dip in the reflection when you hit the eigenmode. Here the same thing. So if you have an energy which corresponds to eigenmode of this very, very complex, strongly interacting systems, then you have some decreasing of reflected intensity or increasing of transmitted intensity, and in this way you can find the eigenmodes of such a complex object, and it is chaotic, and if you so the first object that people studied here is the distribution of spacing between levels. So if so it is something like distribution function of spacing. So you see there are large spacing, there are small spacing, and there is some occurrence of each of them. And you can make statistics, you can count resonances, you can count difference in the energy, and you can see how often some distance appears in the experiment. And what is plotted here is the histogram of distances between resonances, and this histogram appears to be quite interesting because if I try to model it by a smooth curve, so this curve has two features. So one feature is that the probability of having very small distances between resonances, it is not small because simply of small distances, but it is smaller than that. So the probability density goes down to zero. And so this phenomenon is known as level repulsion. So levels in such systems, as well as levels in chaotic billiard, as well as levels in this quantum dot, they don't want to stay very close to each other. They want to be separated, and this is reflected in the statistics that the probability density of having a certain distance between the levels, it drops down to zero. And then, of course, it drops down to zero when the distance is very large, but this is more conventional. And for instance, if the distance between the levels would be completely random, then it should be distributed according to the Poisson distribution, which is just simple exponent. So the probability density is finite at zero, and then it goes down like a simple exponent, e to minus x. What happens instead with these nuclei and billiards and quantum dots is that, first of all, it has a hole here, and it falls down faster than exponential. It falls down like Gaussian, e to minus s squared. So this is a very large difference between the uncorrelated levels. So the levels in such chaotic systems appears to be correlated, and then this correlation is quite quite complex. And the first task of the random matrix theory was to give some universal features of this correlation. I'm sorry, I went different. Okay, and now I come back to this picture of random superposition of plane waves. So if you have a billiard and if you invoke classical trajectories which are intersecting and behaving chaotically, then in quantum mechanics it corresponds to wave function like a random superposition of the plane waves in different directions. So the modulus of K is given by the energy and it is fixed, but the direction is not. And then essentially to the first approximation, when all these scars are not taken into account, this is the random superposition of the plane waves. And this is the very first result in this semi-classical theory of billiards and similar system. It belongs to Michael Berry and Rovnik, and so it has something to do with Ljubljana, as Rovnik was and is here. And so this is the simplest object that describes such a picture. What is important about this object? Suppose I do the following. Instead of this exponent, I take a sum of a random superposition of exponents. And this can be considered like simply the rotation of bases in quantum mechanics. So you know what is the basis in quantum mechanics? The basis in quantum mechanics is the set of basic functions. This set of basic function is plane waves now. So if you take another set of plane waves, you just made a transformation of the basis. So, but since here there was already the random superposition, when you put on top another random superposition, so intuitively you understand that nothing will change in statistical sense. So all the distributions will be the same. So, and this is the main idea actually of the random matrix theory, of classical random matrix theory. So if you want to describe systems like this, you have to invent an object, a random object, such that the statistics of this object does not change when you rotate the basis. And okay, such an object was a random Hermitian matrix, because quantum mechanics has to do with the Hamiltonian. Hamiltonian in general is a Hermitian matrix, and so if you consider random system, so you consider a random Hermitian matrix. So if it is real, it should be symmetric. And then you study the problem of finding eigenvalues and eigenfunctions, and then you are interested in the statistics of these eigenvalues and statistics of these eigenfunctions. But first you have to set the statistics of these entries, because what you have first entries of the matrix. It is symmetric, yes, it is a constraint, but you have some random entries. And then you are interested in the statistics of solutions of the Schrödinger equation. And it appears that the Schrödinger equation makes these statistics non-trivial, even if statistics of entries is trivial. So So first of all, what Wigner has suggested, he has suggested a random Hermitian matrix such as the probability of having certain entries is like this. So what does it mean? It means that you take an entry which is H and M, and you see that the probability of having these entries or some other entries, they are the product of some terms. And we know that if the probability of a set of random variables is a product of probabilities to have each random variable, then these random variables are fluctuating independently. So there is a notion of independent fluctuations and the correlated fluctuations. So when what is called joint probability distribution, the global probability distribution of all these random entries, if it is a product, this means that they are independently fluctuating. If it would be not a product, then they have correlations. So then the next trivial thing is the following. So if I have here the product, this means that entries are independent. They behave like e to h squared. This means that they are not only independent, each of them is a Gaussian random variable with the same variance, which is 1 in this case. But then, you know that the product of something, or product of exponentials is an exponential of the sum. So if I put instead of this product here the sum, then what I obtain is the trace of h squared, because in order to multiply two matrices, so if I have two matrices H, N, S, H, S, M, this means that I have H squared of N, M. Now, if I want trace, I should put M equal N and then sum. So what I will have N, M, N, H squared, and N and sum over N. That will be trace H squared. Now, here, if I put N equal M, I have H, N, S, H, S, N, and if I sum over N, over N, I will have the same as here, but the matrix is Hermitian, and this means that this guy is equal to NS complex conjugated if it is complex, and then it will be the sum of H and S modulus squared. So it will be exactly like this product transformed into the sum, and therefore here there is a trace. This is important. This is important because, as I said, we should, the main idea of random matrices was that the probability of this matrix does not depend on the basis. So if you perform basis rotation, then the probability is the same. So what is the basis rotation? Basis rotation is when you replace the matrix H by the matrix like this, where U is the unitary matrix. So this is the basic rotation. Now, if I have P of H, which is e to minus trace H squared, so I have to check that such transformation doesn't change this probability. And this is indeed the case because of the trace. So if I plug here instead of H this thing, and then to make this simple algebra, so what I obtained, I obtained the following. I obtained U, H, U, dagger, in fact, this is one transformed H. Then the square, the second one is like this, and then there is trace. So this is the unitary matrix, so this product gives 1. And so I have trace of U H squared U dagger. So it still depends on U. But because of the trace, we can make a cyclic permutation. So I can put this U over here because of the trace. And then it will be 1, and the basis invariance is there. So basically, if I have the probability distribution of the entries in this form, I have two properties. One property is that this form doesn't change when I apply the basis rotation. And the second property, which I have shown here, and it is shown also here, that each entry is an independent Gaussian variable. So we have, in fact, very simple situation where the independence of the matrix element is also an independence of the change of the basis. So, and these two properties happen when I have trace of H squared. If it would be trace, let's say, of H to 4, then basis invariance would not be changed, because it doesn't matter what I write here. What matters is that I can do cyclic permutation. But the independence of the matrix element will be lost. It is only for H squared that there is the independence of the matrix elements. So this is the basic of the classical random matrix theory. Then, as I said, I have already said that if I have such random matrix theory, then it is possible to show, and we will do it in our lectures, that, for example, the simplest thing, the distribution of spacing, it has two features. It has level repulsion here, and it has a Gaussian behavior there, and this corresponds to chaotic billiard, which is quantized. So it is classical analog, and after you quantize it, you will get such a distribution. But you can also have an integral billiard which is made of the circles. And then if you look at the trajectories, they are not at all chaotic. What actually was a discovery, important discovery, is that when you have integrable systems, when classical system where trajectories are regular and not chaotic, then after you quantize it and study the distribution of spacing between the energy levels, this distribution will be Poisson, will be just simple exponential, e to minus s. So this is actually a very powerful tool, so powerful that suppose you have some classical systems and you don't know if it is integrable or not, because you know this mathematical skills. What you can do, you can quantize this system, find you know on computer the set of energy levels, and then to see to look at the distribution of spacings. And if the distribution is Poisson, because it is very easy to distinguish between such distribution and such distribution. If it is Poisson, then you can say, well, okay, so there is some hope to invest some time to study analytically this system and to show that it is integrable. If it is like this, like Wigner-Dyson distribution, no way. You say, well, it's not worth of investing time to try mathematical solution.
So there is no classical system without level repulsion?
What I'm saying is the following, that levels are quantum objects, right? So level repulsion is
integrable. Sorry, integrable.
Integrable system with level repulsion,
with
level repulsion, are not known.
Not known.
So that's why I'm saying you take your classical system, or you take a quantum system, and then put it on the computer, and look at the distribution of spacing, and you can immediately say if this is exactly solvable system or not. And if it shows Poisson distribution, the lack of level repulsion, then you take fellow mathematicians. I have found something for you, so you can enjoy. And okay, so now I will give you. Yes.
So here in your ensemble, you take this trace h squared.
Say it again.
In your ensemble, you take trace h squared. So
Yes.
H squared. In principle, if you take h to the 4, h to the any power,
Yes.
it will have the same property that will be
It
invariant.
will be the same property in the sense that it is rotationally invariant.
Yeah.
But we will come to that. That will be, I tell you the answer without proof. But then we will consider such situation. So in principle, you are absolutely right, and I somehow I provoked you. So is it possible to use it?
I guess there is
okay.
a razor.
So what from this derivation, it is clear that if you have P of h, which is exponential of the trace of any function V of h,
H squared.
okay, V of h could be h to 4, could be h squared plus alpha h to 4, and so on. If it is a function of only h and no other matrix inside, all other constants are scalars, then you can do the same thing. You can write V of h transformed is V of U H U dagger, and then you say, well, okay, so suppose it is the sum of powers. Then for each power you can prove that let's say H2n is U after transformation will be U Hn U dagger, and in order to get rid of that, you have to take trace. If you take trace, so you prove that this is the most general form of basis invariance things. But what I'm going to say that this is much more non-trivial case because the entries of the matrix are no longer independent. They are independent only for the Gaussian case, because the trace of H squared I can represent like a sum of the square of entries. And then this sum I represent as product, and then it will be independent fluctuations. But if I take, let's say, fourth power, then I cannot, I lose this property. And answering your question, so that was indeed the question that people start to ask, and serious mathematicians start to ask, what can I generalize? Can I take not H squared but H24, and what will happen to statistics of eigenvalues, of eigenvectors? What will happen then? So the answer, which is not so easy to show, is the following: is that of course, if you add something like this, so then at a finite matrix, so the matrix has a size, okay, n by n. Now, if n is finite, then there are deviations. So if I add h to 4, I will have deviations. But if I take the size of the matrix to infinity, then this deviation will disappear. And this is a great news, because this means that the fact of the trace is much more important than the fact of h squared. Because if I have a finite matrix, then for h squared I have independent matrix element and some nice theory. If I add other powers, then this nice theory will become much less nice. But if I take the limit n to infinity, then these correlations which appear in the matrix element will become not relevant. This is something which is really not trivial, and serious mathematicians invested time for that, and it was not so long ago. It was in the 90s. But then it appears that this is not the end of the story. If this h, this v of h, this is function of h, okay, f of h. If this f of h is slowly decaying for large h, I mean, this of course is a matrix, but suppose that I have a scalar, so okay, then I can have the function which okay, f of h squared is like this. So it is fast increasing, and the exponential of that fast decay. right?
Then there should be
But,
minus.
but I may have the function which behaves, let's say, linearly. This is h. Then I can imagine the function which will behave logarithmically, very slowly. And it appears that, and this is something which I will discuss in this lecture, but this is something that mathematicians are struggling to prove rigorously right now. And there is a mathematician actually who, I think, okay, so anyway, I know the people who are struggling with that right now. And the proposition which actually I made long ago, and now piece by piece they are proven by mathematicians slowly. The proposition is that if this function f is behaving steeper than linear, then correlations do not play a role, and in the limit n to infinity you have all the same statistics. But if it behaves like linear or weaker, then, I mean not weaker, more shallow, then there will be important deviations in the statistics. And actually the most interesting case is when it is logarithmic. In this case, there will be absolutely crazy things happening. And I will show you that the model with logarithmic behavior actually is equivalent to a black hole. Look, I mean, what I want to say is the following, that each good theory, you know, it was Lev Tolstoy, famous Russian writer, who said that any happy family is alike, but each unhappy family is unhappy in its own way. So, you know, rephrasing that, I am saying that any good theory is connected with zillions of other good theories. And any not bad but not significant theory is significant in its own right and is not connected to anything. So therefore, if you have really nice theory, it is not so many of them. They are related very unexpectedly. For instance, I'm talking about random matrices. You ask a question, what will happen when this function is not h squared? And I'm saying that crazy things happen if this function is, let's say, log squared. So when there is not the Gaussian function, but Gaussian in the logarithm, then it's crazy thing which is still to understand for deeply, but one can show, and I have a paper like this, that it is equivalent to the simplest black hole. Okay, now I show a very simple thing, because I will time from time I will be doing some math, because my role actually is the following. My role is to show that random matrix theory is a good theory, in that sense that it is connected with many other good theories which are in physics. But the other thing is to give you some simple calculus that you can not only believe me, but to reproduce it. And one of such simple calculus is the proof that there is a level repulsion. And then you understand what is the, the origin of the level repulsion. So suppose that you are looking for the probability density to have two levels anomalously close to each other. So anomalously means the following, that this is unity here is the average spacing, mean level spacing. This is one mean level spacing, two mean level spacing. And so you have a maximum around the mean level spacing. So the mean is in some sense representative. But you have also spacings much smaller than the mean. And these are the anomalously small spacing. And the level repulsion is what happens with this probability density for such anomalously small spacing. And when you have a big matrix, but two entries of this matrix, two diagonal entries of this matrix are close to anomalously close to each other, then with this anomaly, there will be some anomaly in the spectrum. So this is the anomaly in the entries. But this anomaly in the entries then leads to anomalously close levels in the spectrum. And therefore, if you have such anomaly, it cannot happen, it happens rarely in this matrix. And with this anomaly, if you diagonalize the matrix, you will find two levels anomalously close to each other. But of course, in this diagonalization, the full matrix will come in play. But in fact, it is important only the surrounding of this matrix. So not the full matrix, but 2 by 2 matrix. It is only in the case where these two things are close to each other. If they are at an average distance, then the whole matrix is important. But if they are anomalously close, you can simplify the problem and you can consider the problem of 2 by 2 matrix. So this problem appears in physics trillions of times, and in spin 1/2, in this situation where you have two coupled modes of anything. And in all these cases, so what you have to do, you have to diagonalize this 2 by 2 matrix, and then you find, of course, two eigenvalues. And the difference between these two eigenvalues is plus or minus the square root of that. So this is, one of the most well-known formula in physics, because it tells you that if there are two modes and they are interacting, they repel each other. And this repulsion is this guy. But this guy is random, and therefore, in our case, it is random. So this repulsion can be small, can be large. If this repulsion is absent, then the levels can be arbitrarily close to each other. And then the question is how rarely this guy becomes zero. If it becomes zero very frequently, then the level repulsion will be reduced. If it is it becomes zero rarely, then level repulsion will be strong. And now let us compute. So this is a piece of the computation. And so what I have to do? I have to find the probability density that the distance omega between two levels is this distance is something. Now, it is a general thing. What I have to do to find the probability density, I have to write the delta function. Omega is equal to this, or some other expression in terms of the fluctuating variables. So if these variables are not fluctuating, then I have just one single value, okay? Delta function at 0. But in fact, all of them are fluctuating. So how to compute the probability density of something which is expressed in terms of the fluctuating quantities is just to write down the delta function and then average this delta function over all the fluctuating quantities. This is a general recipe, so whatever you do, it is always so. So you first write your variable in terms of the fluctuating ones, and then write the delta function and then average it. So what means averaging? There is off-diagonal matrix element here. And as we said, every matrix element, which is, let's say, right of the main diagonal, is Gaussian distributed. So this is the distribution of this V. Now, then there is also Gaussian distribution of this and Gaussian distribution of that. But in order to make calculations a bit less involved, I just say that these two things are having flat distribution, not Gaussian, but like this, from minus W over 2 to W over 2. So you can do it with Gaussian as well, but because what is Gaussian? Gaussian is like this. And it falls down very quickly, and you can, qualitatively, you have the same thing as to take it like a rectangle.
Sorry. Is it like common technique to estimate something? Are there, or if I rephrase it, are there some situations where qualitatively it is important to think about Gaussian?
Yeah, there are situations.
Okay.
There are situations, but not this. I
Yes.
mean, there are. What actually is more important like this. So suppose you have a distribution like this bimodal. This is very distant from the Gaussian because it is 0 here. But this rectangular distribution is not very distant from the Gaussian, and therefore qualitatively you can do it. But I simply didn't want to overload you with unimportant features, and therefore I took the flat distribution, which is 1 over W from minus W over 2 to plus W over 2. And then simply a usual integral. So now I have to integrate. By the way, this matrix elements, so matrix is Hermitian, therefore the diagonal matrix elements are all real. This is the property of Hermitian matrix. But off diagonal could be real, could be complex. And these are two different cases. So I write here, for that reason, I write here model square and not simply square. having in mind that I can also cover the situation of the complex V. Now some calculus. This is this formula which I have shown to you, and let us do the following. Let us instead of integrating over the epsilon 1, the epsilon 2, let us integrate over one of them and then over the difference. This is always possible. The Jacobian is 1. So let us then first integrate over the difference.
I'm sorry. In the initial integral, you integrate over the squared with the width of w, but then after the change of
W
theory,
W of order 1. So if you have Gaussian distribution, its variance
okay,
is 1. And if I take rectangle with the variance of order 1, this will be the same thing.
okay, so it's not really important what is the shape of the border, right?
For this particular, almost in all the cases, it is not important.
Okay, because when you change the
Unless
variables
there are
to-
features like 0 somewhere and so on. But you can do the following. You can do absolutely the same with the Gaussian distribution. I simply didn't want to delay the lecture, and you can do the same thing. And we will, this would be a good, okay, so what I will do first, I will integrate over this difference, E1 minus E2, which I denote delta epsilon. So, how this integration in general should be done? So what I have to do, I have to rewrite this delta function as delta epsilon minus solution of this equation. And this will be like this. But, so if omega is equal to, omega squared is equal to this plus that, then delta epsilon is equal to this plus or minus. But then there is a Jacobian. And the Jacobian is the inverse derivative of whatever function stays here with respect to delta epsilon. So derivative of this square root with respect to delta epsilon in the denominator, and modulus because Jacobian is positive. So then I take this derivative and then use this delta function, and then this Jacobian will become like this. So you can, this is a trivial thing. So you take the derivative and then express delta epsilon in terms of that. And you will have, this will be the Jacobian. And then there is a delta function, and then we know how to differentiate delta function. We differentiate delta function. So this W is of order 1, and we are interested in the small omega and small v. And therefore, these limits of integration can be extended to infinity. And then integral of the delta function is 1. So you can do it with the Gaussian, but you have then to deal with all this boundary. I mean, here the boundary can be simply extended. In the Gaussian thing, you can also extend it because there is a separation of the scales. Omega is small, W is small, but the boundaries are of order 1. Okay, then this integral becomes 1, and you arrive at such a form. Now, the integral over dE is trivial because there's no dependence on E. And so that this integral is not trivial. And now let's consider two cases. If V is real, then it is only one real variable, and V modulus squared reduces to V squared, and you have to do such an integral. Now what can I do with this integral? First of all, what can I do? I can rescale the integration variable and to write it as V is equal to, let's say, x times omega. So when I rescale it, this thing will become 1 over square root of 1 minus x squared. So omega is gone. Now, from here, I obtain omega by such a rescaling. And so I will have omega times an integral. Now, since integration here is going only up to omega, otherwise this square root is not real, then and omega is small, then this exponential factor can be replaced by 1. And so, and then after rescaling, after that rescaling, this will independent of omega, and this delta V results in linear in omega term. So the result will be some number times the linear in omega term. And this is for real case. For the complex case, I have to integrate over, then I write V is equal to V1 plus I V2. Both of them are distributed by a Gaussian law. Now, this thing here will be V1 squared plus V2 squared. Now I use the radial coordinates, and the radial coordinates are r dr in two-dimensional case. There is also angular integration which gives here 2 pi. And then I do the same trick, I do the rescaling, and this guy becomes independent of omega, and this guy is small, and exponentials can be replaced by 1, and then because of this thing where V is omega times R and dV is omega times dr dx. Okay. This is then from here after rescaling I will get omega squared. So you see the form of the level repulsion, it depends on whether all their neutrons are real or they are complex. If they are real, then there is a linear behavior here. If they are complex, then we have a quadratic behavior here. And this is well understandable because in order to make the difference small, I have to make small this delta epsilon, and I have to make small the square modulus of V. If V is real, I have to make small only this one and this one, so two variables small. If it is complex, then three variables must be small. Now, the more variables are constrained, so small, the more rare is anomalously small spacing. And the function which is linear, is like this, and quadratic is small. So in fact, in the original work by Wigner, it was only these two cases. But then later on, Dyson suggested some other situation where there are four independent, where this thing here contains four. Why four? Because suppose you have a system with spin 1/2, then the real number is simply V, right? The complex number is V1 plus IB2. So we have this imaginary unit which makes your number two-dimensional, right? But if you have a spin system, then you have Pauli matrices, and then your V can be written as V1 times unity 2 by 2 matrix plus V2 times sigma x plus V3 times sigma y plus V4 times sigma z, and so we have four independent variables. And yes, we have, you say, okay, in 5 minutes.
Yeah, but I mean just the next time or
Okay.
start.
So what I'm saying is that there is a case where there are four independent things, and in this case, we will have in a similar way we will have omega to 4, and this happens when we have spin 1/2 situation. So this is about level repulsion, and then the next topic is about Anderson localization, and this I will not touch today because it is too important. So, you know, to finish that, what we learned that there is a number of physical phenomena where you expect independence of the basis. So, all these physical phenomena can be described by classical random matrices, because the main idea there is the basis rotation invariance. Now, I told you what are these systems? Nuclei, complex nuclei, then quantum dots, then billiards, then shallow water, all this, and a number of others. And this is the classical random matrix theory, which we will study in some more detail. Now, then, there is a phenomenon of Anderson localization, where the basis invariance is broken. And I will show that. And for that, classical random matrices are useless. But it appears that there are some other random matrices which are different from Wigner-Dyson, but still amenable to some analytical treatment. And they are with basis invariance broken, and they can describe some features of localization. And I will give you qualitative introduction next time, and then we go on. So what I'm saying, my goal is to describe some most important features of the classical random matrices, with full understanding that this is a broad class, but not the class that that covers all the universe. There is some very important thing like Anderson localization, and for that we need different matrices. And we will study some of them too. So that is